few more examples, and on these I'm going to say pause the video before I go through them and try them out. So here's your opportunity to pause the video for the first example. Try selecting your U, try going through the work, and resume the video when you're ready to see the solution. Okay, so the strategy here is actually kind of interesting. You would imagine that your u would be 1 plus x squared, and you'll be partly right at points. But you're going to struggle a little bit. So actually what you have to do first is try separating this out, separating the numerator, so it'd be 1 dx over 1 plus x squared, and then plus integral x 1 plus x squared dx, right? We can split the numerator, but we cannot split the denominator. And actually this first one, that is just a plain old arctangent of x. And then plus c, but we'll just add 1c at the, well, we should do it right when we integrate. Okay, fine. All right. And then for the second one, this is where you should use that u substitution. So u is equal to 1 plus x squared, and then if we differentiate that, that would be 2x dx, right, would equal du, but then we don't want the 2 because there's no 2 there, so I'm going to put the 2 over on the other side. And then so we would have plus 1/2 integral du over u. Okay, and that would lead us to a final answer that's arctangent of x plus c plus 1/2, and this would be the natural log of the absolute value of u, right? But u was 1 plus x squared. Okay, and yes, I did two different integrals. Okay, there technically would be two different c's or constants of integration, but they would just add because they're constants, so just having a c in there one time is perfectly all right. So that is our final answer for that one. Okay, so lesson there, if you have multiple things in the numerator, you might need to split it up. Okay, next one, ooh, trig. We love trig, right? Okay, and so again, pause the video, select your u, work it out, resume the video when you're ready. Okay, the u here, I'm going to guess tangent of theta, and then if I do du, that would be secant squared of theta. Okay, does this work? Oh, d theta. This would be integral u squared, and then all that is du. Okay, this time I got lucky. Sometimes I might not. Okay, so then you could work with, I think, if you did the integral of secant, or you set u as equal to secant, it could work. It's just going to be way messy. Okay, so it might not be worth it to go that route. But this u substitution makes it easy because then it's u cubed over 3 plus c, which substituting back in is just tangent cubed of theta over 3 plus c. Okay. So if at first you don't succeed, try again. Isn't that the old saying? All right, next one. Again, pause the video, try it out, see what you get. Okay, I'm going to pick cosine as my u. Okay, you might be tempted to do otherwise, but I'll show you why. I'm going to do u is equal to cosine of t dt. Okay, and then du would be, let's see, negative du would equal to sine of t dt. Yeah, there shouldn't be a dt on the first one. My bad. There we go. Integral. Negative pulls out front. Sine. Okay, so one of the sines gets absorbed from the dt, so I'd still have a sine squared of t, and then I'd have u to the 4th du. Okay, now when I integrate, I only want there to be u's, right? That's the whole point. Like I'm converting to a different variable and finding the antiderivative of that. So I need to convert sine in such a way to a u. Well, u is cosine. Oh yeah, there's the Pythagorean identity. I can do this as 1 minus cosine squared of 1 minus cosine squared of t, right? U to the 4th du, and then that could be written as integral of 1 minus u squared u to the fourth du. Okay, negative integral of u to the fourth minus u to the sixth du, and then find the antiderivative. So it'd be, u, which is cosine of t to the fifth over 5 minus cosine, this would be plus actually, plus cosine of t to the seventh over 7, all plus c. Okay. So with trig, remember to at least remember that those Pythagorean identities are there, and you can convert, sine squared or cosine squared to the other one using that Pythagorean identity. Okay, so the rule, I don't want to say rule, but I'm going to say rule of thumb, or a good trick to try. I don't like tricks in math though. Strategy. Let's go with strategy. If one of the expressions in the integrand has an odd power, and sine and cosine, break it into one and an even power. I didn't explicitly show that here, but it's actually what I ended up doing, right? I broke this into sine of t and sine squared of t. And then this sign, that single sign, ended up being used in the derivative of the u sub. Secant tangent, very similar, but we have to look for odd and evens. If you have a mix, maybe you should look for other strategies. But if they're both odd, generally u is going to be secant. If the exponents on both secant and tangent are even, then we should use u is equal to tangent of x. And if we look back above, that is exactly what we ended up doing, right? U is equal to tangent because we had secant squared and tangent squared as well. Okay, so those are some other strategies to try, particularly around trig. And with that, those are a lot of examples of u subs. Next, we need to figure out, okay, well, we've been working with indefinite integrals. How does this work for definite integrals? So we'll see that coming up.